I'm back! Video 5. Now, you guys realize that all of this is kind of like building the airplane in the air. Okay, so forgive me if we're a little bit incoherent at times. However, minerals, topic 11, guys. That's what we're on. Minerals, topic 11. The first video on rocks and minerals starts off with this guy. Mineral. In fact, this looks like gold, doesn't it? But only a fool would believe that, because this is really fool's gold. And we'll get to that, why this is different than real gold, in a moment. But this is gold, and what is it? Is it alive? No, it's not alive. So is it organic or inorganic? Well, it's inorganic because it's not alive. Is it naturally occurring? Yeah, I didn't manufacture this in some lab. This is naturally occurring. Is it crystalline? Absolutely. I can see the crystals all over it. So is it solid? It is. Solid, okay? Does it have a definite chemical composition? It does. It's called FeS, iron sulfide. Iron sulfide, FeS. And actually, let's just check that out real fast. Its composition, page 16, which is the back page of your reference table. And here it is. Here is what's called fool's gold. We also call it pyrite. Can we see that okay on the camera? Or should I turn off the lights? Let's turn off the lights. There we go. And here it is. And actually FeS2. Forgot the 2 there, Critelli. FeS2. What are those things? Those are called elements. Fe stands for iron. Let's say you're a little bit weak on the Latins, like I am. You can go down here. And what does it say that Fe is? Here it is. It says Fe is iron. Look at this. Reference tables say all, guys. About 35 questions are going to be on that final exam, if indeed we have a final exam this year, okay, on the reference table. There we go. So what is it? It is an ore of sulfur, because it's got some sulfur in it. It's got iron. It's FeS2. It's called pyrite. So what am I getting at? It's a definite chemical composition. So what is a mineral? It's an inorganic, crystalline solid of definite chemical composition and structure. What is a mineral? An inorganic crystalline solid of a definite composition and structure. Got it? Good. Okay, that's what you have to know. What are minerals made up of? Minerals are made up of these guys. What are these guys? Chemistry. Elements. Okay, don't worry, we're not going to go too heavy on this. These are the guys that are in what part of the earth? Well, they're all over the earth. But where are the minerals? They're in the air, they're in the sea, they're in the land. But where are the minerals mainly forming? They all start off with something we'll talk about with the formation of rocks. They actually all mostly start off with magma. And they form in the ground. They form in the lithosphere. So here's the deal. A lot of these, well, all these to some extent, are found in minerals. So elements make up minerals. What do minerals make up? That's right, minerals make up rocks. Elements make up minerals, minerals make up rocks. Question on the final exam. Do most elements on that periodic table of elements make up minerals? Well, let's see. Page 1, Earth Science Reference Table. Do most elements make up minerals? Actually, the answer to that is no. Out of over 100 elements on a periodic table of elements, really, what do you have to know that are found in the crust? 1, 2, 3, 4, 5, 6, 7, 8. Only 8 are common in the crust to make up minerals. Only 8 out of all those elements are common. Now, there are some oddballs, like sometimes silver likes itself, and silver is just pure, and you get silver. And sometimes gold is just pure, and you get gold. But the reoccurring elements, 8 of them are reoccurring to commonly make up minerals. What's number 1 and number 2? Well, I'm going to show you number 2. Number 2 is one that's a silvery, slimy metal called silicon. By mass, that is. Number 2 in abundance by mass. You're going to be asked, hey, what's the second most abundant element to make up minerals? Do you have to memorize it? Of course not. It's silicon, 28% by mass. What's number 1? Oxygen. So now you're really confused. How does air mostly make up rocks? Well, it is an air when it's combined with metals. You know, like rust, a form of chemical weathering in the last unit, oxidation, Okay, well, iron seeks out oxygen. Silicon seeks out oxygen. Silicon and oxygen get together to form the most abundant mineral on the planet. Silicon and oxygen, actually the most abundant minerals on the planet, called the silicates. And actually it's an oxide, but it behaves like a silicate, and that is the mineral called quartz. Can we see it? This is quartz. And quartz is a mineral, if we go back to that last page, come on, you guys got to work with me. Back to the last page, here's quartz. Down here, it says quartz. Sorry, there's some stains on this paper. There it is, quartz, SiO2. What's it made up of? Silicon and oxygen. In fact, anything that has Si or O combined in it is called a silicate mineral. And here you have a silicate, and there you have SiO silicate, and there you have SiO silicate, and right up there, where it says fluorite, that's not a silicate, because there's no Si and O in it. But Si and O are the most abundant elements in the crust by mass. If you were asked by volume, you could clearly answer that, but usually you're not asked by volume. You're asked by mass. And I said silicon and oxygen. I gotta tell you guys a little sidebar story here. This silicon stuff, we never find this in nature. In other words, it doesn't form by itself like copper or like silver or like gold. This is really cool because this is silicon metal, not silicone for like augmenting operations for females. This is silicon. Silicon is a metal that doesn't occur on its own. It only occurs in combination with other elements, specifically oxygen. So someone figured out that if we cook up a piece of quartz, which is made up of Si and O, and we drive all the oxygen away, we're left with a silvery slime. And then they figured out that that silvery slime is super conductive. We can super ductile, which means you can draw it into wires. Super heat resistant. That is the number one, or now with cobalt and everything, number 2 metal used in the computer industry. In fact, this silicon, which doesn't occur on its own, which has to be cooked out of quartz, it's got a whole valley named after it, Silicon Valley. So very, very special. And in one way that minerals are so special. What other ways are minerals special? Well, you can have a super soft mineral. Let me turn on the lights. Wait there, guys. All right, I'm coming back. This is called talc, the number 1 mineral for the cosmetic industry. Super, super, super soft. It's in all your shampoos. It's in all your soaps. It's everything like that. We also have this one right here. This is called rock salt. This is used on your French fries and stuff like that, and all your foods. This is actually salt found in the ground. It is a mineral. Rock salt is when it's impure. The mineral name for it is actually called halite. The only difference is rock salt is impure halite. Halite is the pure mineral. We also have a mineral called calcite. Now, if you noticed, all these minerals are like different. Here's a mineral called malachite. This is made up of special waters filled with copper. That's why it's tarnished all green, that come out of magmatic waters in geothermal areas. Throwing a lot of words at you right now. I know, it's okay. All right, and then we have pretty quartz, sometimes amethyst quartz, sometimes citrine. The way I remember this kind of like reminds me of urine. So it's like latrine, citrine. You might have another way of remembering it. That works for me. Okay, the thing about quartz is, quartz could be like this. Quartz could be like the citrine. Quartz could be like the amethyst. There's rose-colored quartz. There's all different kinds. Color really isn't a reliable identifier for quartz because it's so variable. Color, although it is a physical characteristic of minerals, is not reliable on its own. We need other things. So to do that, every mineral, based on the way its atoms get together and structure the mineral. I'm going to say that again. Every mineral, based on its atomic structure, the way the silicon and oxygen get together, the way the iron and sulfur get together, the way the atoms, the elements are combined atomically, the atomic structure of the mineral really develops all the physical properties of the mineral. How hard it is, how hard it is. How hard it is actually, I was tapping my finger, that's really wrong. How hard it is actually how well it scratches other materials. For instance, if it scratches glass, it's harder than glass. If it scratches a penny, which is mostly copper, it's harder than a penny. And that's actually called Mohs hardness scale. So you see hardness on page 16. You also see if it leaves a streak on something called a streak plate. That's really the true powdered color of the mineral. Again, due to its atomic structure. The true powdered color of the mineral is left on a streak plate, and that's called streak. Also, there's this thing called, well, actually, I want you to take a really close look at this. Guys, are you looking at this? Guys, looking at this? Because in actuality, right here, what you're seeing, for many of you, in your lifetime, may be the best cleavage you ever see. Now, what is cleavage? Of course, I'm talking about mineral cleavage. What is cleavage? It is the way the atoms are structured so that if a mineral breaks, it duplicates its same formation. In the case of calcite, every time this is struck, it will break up into little parallelograms. You might even call them rhombus shaped. And every time it's struck, it will break like that due to the way the atoms go together. With halite, it's different. With halite, it breaks up into little rectangles or cubes every time. The way a mineral breaks with biotite mica would actually break off into sheets. As you can see, these are like layers. It's called sheet cleavage. So the way a mineral breaks, which is controlled by its atomic structure, very much is an outstanding property of what the mineral is. We can tell the difference between halite and calcite just by their cleavage alone, really. And then we can tell by the other properties of hardness and streak and luster. Luster, whether or not a mineral looks like a metal. For instance, let's take a piece of olivine. I always know this because it's olive green. Olive green, olivine. Olivine doesn't shine like a metal, so it's not a metallic luster. Biotite. Well, biotite is shiny, but I wouldn't make a chain out of it to wear jewelry. It's not metal shiny, it's just shiny. But then there is that pyrite. And pyrite, let me put it in the light. Pyrite is shiny. Look at it. Shiny, okay? It's shiny like a metal. And because of that, it has what's called a metallic luster. Once again, all these properties of the minerals are all decided by their atomic structure. Now let me show you the number one atomic structure going is made up of that silicon and oxygen. So silicon and oxygen form together. Actually, if you were to break it apart, it sort of looks like this in a cartoon drawing, which sort of forms like a pyramid of 4 oxygens and 1 silicon stuck in the middle. Because of that, it's not something you have to memorize, but you have to recognize. You have to recognize what's called a silica tetrahedron. Silica, 1 silicon, tetra, 4 hedron gases. Okay, so it's 1 silicon, 4 oxygen molecules to make up this number 1 building block of minerals. And it's no surprise it's the number 1 building block because it's made up of silicon and oxygen. And what's number 1 and number 2 in the crust? Silicon and oxygen. And once again, the way those atoms go together is what really controls the structure and the physical properties like hardness, luster, cleavage, streak of a mineral. Next topic is minerals make up rocks, and we'll show you how that's done.